Let's use this graph to answer some questions. So this is a rocket that was shot up into the air. It says the propellant burns for a few seconds, accelerates the rocket upward, and then after the fuel burns out, the rocket coasts upward for a while, then begins to fall. Then a small explosive charge pops out, a parachute breaks the fall of the rocket. But this is a graph of the rocket's velocity. So this is a derivative graph. This is telling us essentially how fast, although it also has a direction component, the rocket is moving at any point in time. So the first question, how fast was the rocket climbing when the engine stopped? Well, I'd say that when the rocket started over here at 0 seconds, it was moving pretty fast, and as the fuel began to burn, it was moving faster and faster and faster until right about here, the engine, the fuel burned out. And that looks to me at like it was 190 feet per second. That's how fast it was going at that particular moment in time when the engine stopped. How many seconds did the engine burn? Well, it looks like it burned from 0 to 2 seconds. Then it stopped. So I'm going to write the numbers here. This is 190 feet per second, and it looks like it burned for 2 seconds. When did the rocket reach its highest point, and what was its velocity then? Now this is where you kind of have to stop and think for a minute. So the engine stopped right here, and the velocity started to decrease because there's no more fuel being burned. The velocity started to decrease, but the velocity is still positive. So it's still going up. In fact, it's going up right until there where the velocity hits 0. So remember, this is the graph of the derivative. And as long as I have a positive number here, it means that in my graph of distance versus time, as long as I have a positive number there on the derivative, I still have a positive slope. And I have a positive slope until that slope hits 0. And if you think about how a rocket would go up, it might go straight up, and it might go to this side, but it would take the shape of a parabola. So it's when the velocity hits 0, when the slope of my derivative hits 0, that I've reached its highest point. And that was at 8 seconds. And as we said right here, its velocity, its slope, was 0. So once it reaches its highest point, the rocket starts coming down to Earth. And if you remember, velocity has direction associated. It's not speed. Speed is the absolute value of velocity. So velocity has direction associated with it. And now my velocity is negative. The slope of my derivative is negative. I'm going into the negative part of the derivative graph. So my velocity is negative, and it looks like it reaches a velocity of about negative 90 feet per second. So it's going downward at negative 90 feet per second, and it looks like that is just about between 10 and 12, just about 11 seconds. So at 11 seconds, that parachute pops open. So how long did the rocket fall before the parachute opened? Again, the temptation is going to be to look at this graph and go from here to here, but that is not correct. The rocket has fallen from where the highest point was, where velocity was 0. So the rocket was only falling from 8 seconds to 11 seconds. So the rocket was falling for 3 seconds before the parachute opened. And I'm assuming that this is where the parachute opened, because although the velocity is still negative, it is still falling, it is slowing down how quickly it is falling. So the rate at which the velocity is changing, the velocity is going downward, but it's not speeding up going downward, it's now slowing down going downward. So you can kind of see and think about why it is at 11 seconds that shows that the parachute popped open. The last question asks, when was the rocket's acceleration the greatest? And acceleration, so if we have our distance, s, is a function of time, well, our velocity, we know, is the derivative of s, and our acceleration is a derivative of velocity, or the second derivative of s. So this is the graph of my velocity, and I want to find out where the acceleration was greatest. I would make a graph of the derivative of this, and I'm looking for the slope of this graph right here. Well, it looks to me like the slope is the most positive right there. So that would be where the acceleration was the greatest, right about when the engine cut off at 2 seconds. So it was greatest right here at 2 seconds. When was the acceleration constant? Well, if you look at right here, the slope of this line right here is a constant. It's a constant slope, it's linear. So the acceleration was constant when the rocket was in free fall from 2 to 11 seconds. So 2 to 11 seconds was when the acceleration was constant.